I'd like to welcome Dr. Bernhard Riecke, please.
All right.
Thanks. Take it away.
Thanks, Patrick, for having me, and I'm excited to have such a large audience here. Yeah, I just want to bring the slides a bit closer so I don't have to sit over there and you have to look at the slides over here. So what I'd like to do today is basically give you a bit of an overview, actually a fairly fast-paced overview of all kinds of different issues and also interfaces for navigating through virtual reality. Before I do that, so I work at Simon Fraser University. I lead the iSpace lab there down in Surrey. So if you take the SkyTrain to almost the very end, that's where we are. So there's a whole lot of different navigation interfaces for all kinds of different purposes. And what I'd like to do today is give a bit of an overview of the different issues and basically trying to figure out how do we really travel and navigate through virtual reality, computer games, and so on. And talk a little bit about the different tasks and specific interfaces that are suitable for certain tasks. How do you, so the main question is really, I mean, in reality, we just walk. It's natural. We have our hands available. It's low cognitive load. It works. Spatial orientation works. I can easily do that. I still know my computer's there. My audience is here. If that doesn't work, we have a problem. Try doing that in a computer game, or in any virtual reality setup right now that's not free space walking. With a joystick, you certainly get lost. And you, with all, the other thing is you wouldn't even have your hands free. So there's a couple of problems, I would argue. I mean, these interfaces are great. But imagine a real-world scenario, for example, where you want to give people an impression of the new wonderful building you're designing. So you do an architecture walkthrough. You have a group of people. You need to pay attention, see how they're interacting. You want to gesture. You want to point out things. You need to open doors. All kinds of things you want to do. And the least thing you want to do is spend any effort or any hands on walking around. And this is where the classic interfaces don't really work. And sure enough, you can use free space walking if your tracking system should ever be large enough. But even for those, you typically run either into a wall or some limitation, or you trip over a cable. So there actually are quite a few problems there. Especially in virtual reality, I mean, you're all about motion sickness. Actually, who has experienced motion sickness before in virtual reality? Okay, if you have not, go down to the floor and try it out so you know what we're talking about. It can be quite severe. I'll talk a little bit about this beforehand. Other issues we have is really in terms of accuracy. How accurately can you actually navigate through the environment? Precision, can you really do that smoothly without ever bumping into things? I mean, if you virtually bump into things, that's not as critical, but imagine a telepresence application where you're controlling a drone or big robot walking remotely. You really want to make sure you don't run into things, that it's smooth. Learnability is a huge issue, especially if you want to bring it to the mass market. No problem for experienced gamers or VR enthusiasts. Yes, they can figure out just about any interface, but that doesn't fly if you want to really have a mass market. Naturalism, believability. If you want people to experience, for example, let's say virtual tourism, the actual scenery, what you don't want is they have to fiddle with the interface and be concerned with that. You want them to be really paying attention on that. When we naturally walk, we perceive self-motion, which makes sense. It's really important for remaining spatially oriented. If you're just looking at a small screen, you don't. I mean, the only commonly known screen where it really works well is IMAX screens, basically, where the field of view is so wide that you feel like, oh, I'm actually moving. Why don't we try and create virtual reality where even without having these huge free space walking areas, we could actually provide you with these cues? Really important for applications is, of course, real-world transferability of the results. So if what you do in virtual reality, let's say flight simulation or NASA training or any, obviously lots of military things, but even simple things like operation, how to disassemble this copying machine, if that doesn't transfer into the real world, there's an issue. And yeah, I already gave you the example of being a tour guide. So, well, let's start with the bad part, so adverse symptoms. What do you think makes people really sick in virtual reality? Any thoughts?
Can you ask that again?
What makes people sick in virtual reality? Why do people actually get motion sick?
Incongruity between what you think should be there and what is there.
Yeah, so there's anticipation. Yes. Any other thoughts? Yeah.
Like if there's like a delayed reaction.
Yeah. Delay is huge. I mean, this is getting a lot better just over the past few years. Any other things that come to mind? Yes. Yeah, perspective? Yeah. if there's a bit of a mismatch, you move your head and the visuals get like, not good. Yeah. Lack of physical feedback, yeah, it's a very important one, especially thanks for the pitch, in terms of navigation interface. If you don't get any vestibular cues or proprioceptive movement cues, it's an issue. There's another one. It can, yes. Especially if you're fast moving, then by definition, if you only have, let's say, 20 or 30 frames per second, it's always going to be behind. So that's why higher frame rates are important. So yes, there are a lot of issues, and there's also a lot of different symptoms. It can range from nausea, dizziness, stomach symptoms, cold. You can be cold, hot, pale, red. Vomiting is kind of the ultimate indicator. So if you're at that level, it's kind of too late. It can get worse over time. So depending on the application. And there's different time scales. People try to predict it and simulate it. It's quite tricky, actually. So just one word of caution. If you ever just feel the onset of motion sickness, stop immediately. Don't try to go through it. It can really have lasting effects. It can last for an hour. It can last for 6 hours. I mean, literally, like a colleague of mine was like, oh, I'm just going to finish that trial. And then 3 hours later at his desk, he was like, I have to go home. So it really is a problem. There's also eye-related issues, eye strain, difficulty focusing, blurred vision, these kind of things. So a lot of issues. Headaches, of course. So definitely suggest drink a lot of water. Apparently ginger helps for some people just with normal things. Difficulty concentrating. So it's a whole lot of different things. It's not just like seasickness, which is a bit more limited in terms of different parts. There's also more moderate issues, often called the dissipate syndrome, like difficulty concentrating, drowsiness, fatigue, apathy, and there's more. Another thing that can happen, especially if you want to do simulator training or, let's say, driving training, you can adapt to the simulation, and then if you want to go back in the real vehicle, this might actually be an issue. I mean, for some military applications, they don't even allow people to drive for a few hours after they come out of the simulator because you need to readapt to the reality. Another issue that can happen quite a bit actually in virtual reality is disorientation. In computer games, often they are designed so you can't stay oriented. By the way, if you don't want to, you don't have to take pictures of the slides. They're all on the web. I'll show you the link in the end, so you can download them. But you're welcome to take pictures. But part of these slides are part of a longer 3-hour presentation we gave at an IEEE virtual reality conference. So you get even more detail if you download it. I'll have the link at the very end. Sorry, have to stay until that. Also, reduced performance can be an issue in terms of adverse symptoms. One question that we sometimes get as virtual reality research is whether self-motion perception is really an issue. So you having the embodied sensation that I'm moving through the world. And just like in normal driving, that by itself doesn't cause motion sickness. The motion sickness is caused by harsh accelerations, kind of issues in terms of what we mentioned, frame rate, delays, display, different expectancy, missing vestibular signals. It's kind of like, sure, if you don't get into a car, you won't get sick, but just getting into a car and driving doesn't make you sick. It's a kind of maneuvers, and it's very similar there. So if you look at in detail into the literature, there's clear indication that basically there's not a strict correlation between getting the illusion of self-motion and getting motion sick. Of course, what we do notice, if you're just using, let's say, a 3D CAD model on a small screen, you can move that around fairly quickly, which is important for modeling, and you won't get sick because you don't really feel like you're in there. If you try doing that in a cave or in a head-mounted display, yes, you will very likely get sick because the interface is not built for that. So reducing the field of view is the one thing that helps the most, but often enough you still want to see it realistically. So what can you do? I'm not going to go through all the theories. If you're interested in that, it's in the full tutorial slides. But just very quickly, so one of the things to not do is really these ship-like slow up and down frequencies. So there's wonderful research actually investigating what kind of frequencies make you the most sick. Great research. What you can also do is sometimes people can adapt to repeated exposures, but so sometimes people get better over time, but it can also have the opposite effect that you just get conditioned as soon as you see that stimulus, you get sick. It's kind of like food poisoning. Reducing inconsistencies, especially things like latencies, that is really, really important. Lag, distortion, flicker can be an issue. Reducing accelerations and jerks. With jerks, I mean the fast changes in acceleration. Head movements. So if you do head movements in virtual reality, what should happen is exactly the same that should happen in reality. The world appears stable, which is fine when you have a projection screen. You don't need to do anything. When you wear a head-mounted display, you need to immediately counter-rotate the simulated scene. Otherwise, there's a problem. And that's where the delay and tracking and so on was for such a long time such an issue. Now, finally, the commercial-grade head-mounted display have caught on, and it's getting to a point where it's almost good enough. So it's getting really close. But basically, try not ever to use your joystick to move the camera when you have a really immersive wide field of view display, because normal joysticks would be way too fast. So there's lots of issues there. Active navigation control can help, and as you mentioned, at least some minimal physical motion cues. I mean, if you just have a simulation of a small environment, yes, you can just do free space walking, that works, but it doesn't work if it's a larger building, basically. And I'll talk about some techniques how you could get around that. And there's, of course, lots of further information and books on this. So why look into travel techniques? I mean, in a way, you could argue that just about anything we do in real life, often you move your head a little bit, you move your body to just get a different point of view. So it might really be one of the most common universal interaction tasks. Pretty much for all 3D user interfaces. But one thing to keep in mind is that often it's not the travel itself that people really want to do. Typically, you walk somewhere because you want to talk to somebody, you want to interact, you want to do something. It's typically not the walking itself. Normally that should really not require that much cognitive resources unless it's part of let's say, a ballet performance. But other than that, typically you just want to get there, do that, and not spend much time on it. You want to have a conversation and do something. So what are really the different travel and tasks and techniques and so on? So just very quickly, there's different kinds of tasks, like exploration, search, and maneuvering is one way to categorize them. And for exploration, when you don't really have a specific goal in mind, you just want to get a feel for where things are. It's really about getting information, so you want continuous direct control, ability to stop anywhere, look around. Searching is a bit more different, so you have something specific in mind, so you might want to get there fast and quickly. Maneuvering is when you, for example, when you have to avoid different obstacles, driving in traffic, or here at a conference, try to find your way through that. So for these kind of things, you really need a nice balance between the speed you can achieve, high usability, and really frustration with the interface is really tricky. So has anybody ever tried one of these like conference robots? One of the challenges is you don't have a rear view camera, and you see a lot, but you typically don't see exactly what's around you, and you sometimes can have the same issue in VR. So just another way to look at different travel techniques is basically look at, okay, what is actually being moved? The most of the applications are really about self-motion. So first-person view, especially when people talk about head-mounted displays, all kinds of steering interfaces, there's more that I won't talk about. Object motion is, for example, where you grab the object and bring it towards you. That is actually quite a different movement. So where you move the world coordinate systems. That's what you often do in the editor when you do 3D modeling. Or you can move the camera, basically. That's typically in a third-person control. What I'll talk mostly about here is in terms of self-motion, so fully immersive environments. Another way to categorize them is in terms of the amount of physical and vestibular motion cues. So full physical motion is, okay, 1 physical meter is 1 virtual meter. So free space walking, for example. Then there's interfaces where you get a little bit of motion cues. So for example, motion platforms, some treadmills where you get a bit of motion cueing. So you get a little bit of these cues. Whereas if you just use a joystick, gamepad, these kind of things, there's not really anything in there. Keyboard, so basically fish tank VR. So how do you design these travel techniques? I mean, the ultimate goal is really to be able to free roam in large virtual spaces, have high overall usability, suitable user experience, be unencumbered, intuitive, effortless. So it's kind of like second nature, just like walking. You don't have to think. I mean, we're not really good at multitasking as humans, but we can always walk while we do something else. At least most people can. Believability is also important for some applications. And in a way, the navigation should be natural in the sense that you get at least the important cues that you really need for a given task. And keeping in mind that the navigation itself is often the secondary task. It's really in order to get to a goal or to interact with something or somebody. And constraints are, I mean, physical space is always a constraint. Even in the largest free space walking areas, there's typically some kind of wall, some kind of limitation, tracking area limitations. Even if it's a wireless system, then you have problems with Wi-Fi, reachability, and so on, technical complexity. So what I like to do is go over lots of different solutions, often fairly quickly. Feel free to ask any questions in between if anything's unclear. Otherwise, we'll have also some time at the end. So free space walking areas. So this is some classic setups basically that you might have seen. So they allow for fairly natural walking, but if you really look at how people walk, it's typically a bit slower because they're still a bit afraid. Especially if the tracking isn't perfect or they have seen the place before, they know there's an object there in the place. So, but you have fairly naturalistic biomechanical cues. There's other ways to do it, just like redirected walking. I'll talk more about this. Scaled walking, especially if you run into walls. Issues are, okay, often you still need to wear a backpack or cables. It's getting better with the technology, so this will get better and better over the next few years. The weight is going down. One thing to consider is actually, do your users really want to spend the effort of actually walking? If it's like if they would have to walk for half an hour, is that something they would really want to do? I mean, if you look at out there, most people actually prefer driving or taking transit instead of just walking long distances. So just be sure that people really want to move. I mean, many of these headsets are getting wireless now, or it's getting close, so that's good. In terms of the metaphors for walking, I mean, there's full walking where you have your natural gait cycle, so the walking cycle. There's partial gait cycles. Basically, people do some kind of walking in place. I'll show you some examples later on. And there's what's sometimes called gait negation techniques. So you walk, but the treadmill or something is pulling you back. There's some really interesting low-cost examples. I'll focus quite a bit on more low-cost examples, but still show some of the fancy ones just for the fun of it. So redirected walking. Has anybody tried redirected walking? Okay, good. I'll try to give you some videos to illustrate this. So the challenge is really, what you do is you have a free space walking and there's a wall. You obviously want to prevent the user walking into the walls. And one thing that people have been doing for a while is basically redirected walking. So whenever you would run into a wall, they ask you to stop, turn around, and often what they ask you to do is basically instead of so in terms of going back away from the wall, they need you to rotate 180 degrees, but they put in a gain factor. So I think I can show this in the other video as well. So basically, what you see here, the blue square is the physical space they have. The overlaid one is the environment through which it navigates. So basically, whenever they would be running into a wall, you ask them to stop, rotate, and then they think they rotated, for example, 360 degrees, but in reality, they only rotated 180 degrees. So you can basically, with lots of stops, you can walk indefinitely. It's just not the most natural thing because, well, you have to stop somehow. But there's a whole lot of research in this, actually. And it's nice in the sense that you can walk the whole way. And there's more interesting research in terms of, well, okay, can you also just kind of slightly, if you know there's a wall coming, why don't you just tell them to make a curve physically, but visually they believe they're still walking straight forward. And you can do this with walking and with a wheelchair and so on. And if this space is large enough, this actually works in the sense that people don't really perceive that they are being moved sideways, especially with a little wheelchair that works. With physical walking, it's a bit more difficult. So people came up with all kinds of different metaphors for doing this. So for example, here's an illustration for one example. So basically, users there, you see it's a really small space, so they go into this kind of like special teleport area, and then they rotate around. In the visuals, they believe what they see is that they turn around 360 degrees, but physically they only turn 180 degrees. So this way they can just kind of keep going back and forth and basically go indefinitely. But it's not the most natural thing. And so you can try all kinds of teleport metaphors, like being picked up by a bird or whatever. So people try all kinds of funny things. This is one that is kind of interesting, where you don't get any visual cues, but you get haptic cues. So you kind of walk around this, and if it's large enough, then you feel like you're walking along a straight wall, and you're just keeping your hand sliding there. So if you go to SIGGRAPH, IEEE VR, these kind of conference, you get to try these out, and it's quite interesting. So it's basically haptic and visual redirection. And you can imagine you can create fairly large environments this way, especially if you have a block raster. So how do you do this if it's really important that people walk? So here's some implementation guidelines. Definitely try to avoid perceptual conflicts as much as possible. So as soon as people notice there's something going on, you often have a problem. Either they get sick or usability goes down, or they might just not walk fast anymore, but be really very careful because they notice something's going on. So try to avoid orientation changes as much as possible. And there's interesting research basically telling you how much specifically you can turn people without them noticing it. So for example, users could be turned physically about 49% more, 20% less than a displayed visual rotation. So it's not a huge range. You can mess a little bit with it, but not really too much, otherwise you do notice. For translations, it's even less, so you can mess only so far with it. So 40% more, 26% less. And users will perceive themselves walking straight in a virtual environment while being continuously redirected on a circular arc if the arc's radius is greater than 22 meters, so a lot bigger than this place here. So even there, if you really want to do this, you need a large space. And so there's quite some limitations. So you need a large tracking space. Smaller spaces, it doesn't really work that well, and people might just ignore it. You have these wonderful cues what they should do. If they ignore it, they can still run into the wall, and there you have the technical problem. So you might still some physical safety setup. And if it's too much redirection, actually the cognitive resources are higher, so it's not as intuitive. It doesn't have the, okay, it's supernatural, I can always do that you'd really like to have. So what else can we do? I mean, one thing you can do is just simply scale the walking. Like for example, if you know your virtual space is 10 meters wide, but I only have 5 meters, why don't I just scale it up? So each step I take is twice as far in the virtual environment, which you can do, of course. But that's a bit of a problem, especially with head tracking. But you have the full gait cycle, so it's fairly natural, but it does certainly increase motion sickness, so not such a great idea, and it's not as easy to use. So what some people try doing is, well, maybe you just do normal walking naturally. So here's the normal walking speed, physical walking, virtual walking, and if they run or go faster, then you increase the virtual speed by an additional factor. It's kind of like 7 league boots, basically. So that works. You just need to check a bit, for example, that the head bombing and so on is one-to-one, so you don't scale everything. You only scale the one direction that you really want to increase. So it's an interesting solution, works for certain application. It's still a bit unnatural. The difference is perceptible if the gain is more than like 35% more, and you still have a limited area, and you still need to make sure that people go fast when you want them to do that. So what else can you do? I mean, people tried a lot of these walking in place techniques. So here's one, for example. So somehow you need to track where your legs are, so you can either measure this directly or use a Kinect or whatever kind of tracking system you can do. And the idea is, okay, depending on how you walk and which direction you go, you walk forward. So as soon as you do this kind of pseudo-stepping, marching movements, you walk forwards. And if you go faster, then you go faster, so you can try different things. So lots of interesting ideas there. And the most common of these techniques is walking in place, really typical, some kind of marching gesture. There's others where you can do tapping or wiping, all these kind of things, which are a bit less strenuous. And so on the positive side, I mean, you have the normal exertion. It removes the size limitation. This is used highly in caves, basically, if you don't want to use a joystick, so you can still do this. It enhances presence, so that's good. But it's still not super natural, really. You don't really feel like you're moving, so you might wonder why go through the effort of really doing these kind of pseudo-walking. You actually have more exertion than for real walking. And it's not as effective as natural and real walking. But, I mean, if you look at the Unity App Store, I mean, there's even very cheap versions of doing this, which basically just tracks the IMU, so the inertial measurement unit, off your phone. And basically, as soon as it detects this bouncing, you just kind of move in this direction. So this can be super effective and cheap if you don't have a joystick. I mean, that's like when you have a Gear VR and you don't want to touch it, or just a simple Google Cardboard where you don't have any additional interface. You can do platforming games and things like that, so it's certainly possible. Another possibility is to use gait negation techniques, so where basically you're being pulled back, even though you're normally moving. So here's a really old description of how an ideal setup might look like. So we can have linear treadmills. Omnidirectional treadmills are a lot harder to make. I'll give you a few examples. You can have low friction surfaces, step-based devices. I'll show you some in a moment. So the classic is linear treadmills. You can also do them for zero gravity and low gravity. So there's a whole lot of different research going on in how to do these. One of the big questions, of course, with linear treadmills is, yeah, they work great as long as you're only going forwards, but how do you actually turn? And how do you really create a believable rotation? And I mean, yes, you can just rotate the whole treadmill, and of course, people tried that. It's not quite as cheap anymore, and you get the vestibular cues, but you don't get the cues in your feet that you're moving. So you're still missing something. It doesn't really feel like the real thing. And even for that, like, what if you just want to step to the side to avoid an obstacle? Or, I mean, when I'm moving here, I mean, often I would just do this. You cannot do that on a linear treadmill unless it's a really wide one. Or how do you go uphill? Actually, for going uphill, there are solutions. So you can tilt this, so you can buy this if it's in your budget. If you do this, what's really important is to be tethered and safe there, as you can imagine. And this actually really adds a lot to the realism of the walking. So you have a special harness. It's not just a simple one you can quickly build yourself. But if you have that and add the force, then you can go uphill and downhill. For these things, the other thing you need is basically a safety harness also in case you fall. I mean, it's not too bad if you have just a projection, but imagine you have a head-mounted display on and you're falling. I mean, this is terrible. You're falling on a treadmill. So you really want to make sure that it's an absolutely safe system. But if you do something like that, the biomechanics of walking are actually really, really close to real walking, which is quite amazing. I mean, there's still limitations, like, okay, you can quickly go down, you can only have flat surfaces, and if you want to use a projection system, it's still complicated. So people came up with other ideas. I mean, for omnidirectional walking, how about just walking on this kind of roller carpet? So here's a prototype of that. It doesn't really scale that well, and it still feels like you're actually walking on little rollers. But it exists. Here's another somewhat scary setup. That's a tourist treadmill for omnidirectional walking, where basically you have two conveyor belts, like a large one and then small ones on that. And I think this is really bold to wear these little sandals when you do this, without having any safety system there. But the really cool thing is you can walk indefinitely in all directions, and you can do, I mean, this one is so small that you cannot really do large steps, because otherwise you would almost like fall off or get your toes in there. but there are larger ones that you can have there. So this is how it really looks like without the safety system. So the nice thing here, it looks really safe. So, but if you look underneath, it's a massive construction. So it's more like $1 million and upwards. And again, you need a safety helmet. But what is nice, it's so large that you can start walking for a meter or so before you're being pulled back. So you actually get some vestibular motion cues. So this is quite an amazing setup. That one currently, I think, is out of commission because it had technical issues and it was so expensive to repair it. So it's a bit of an issue. But people tried other things. So here's Cybersphere. It's like a hamster ball, but you're being inside. They also tried the opposite, where you're outside, but that's even more dangerous in terms of falling. So it works. I mean, the problem is you cannot really have a safety thing. So this harness here just is kind of rolling freely on the system. And now you might wonder, how do you actually get out of this? Because it needs to be closed if it needs to rotate in all directions. And you can imagine it's kind of hard getting all the computer gear in there. So everything ideally needs to be wireless, or somehow you need to get electricity in there and a big power pack. So also walking in that, I mean, the problem is it really feels like you're walking in a hamster wheel. So unless that's your application, it does not feel like you're walking. And now watch how he's getting out of this. I mean, you really need special training to elegantly get out of this, because if you walk in this direction, I mean, it goes down. So, and you can only get out at a certain angle. So it works. It's an amazing setup. But it's not the kind of thing you want to have in your living room. And there's a few really interesting ones. Some started on Kickstarter. Like here's the, which one's that? Virtualizer. And the idea is basically you have a safety harness that also prevents you from fully falling. You have to put this on. But this one, the idea is basically you have a super slippery surface and you wear socks or anything that's super slippery. But you could, in principle, walk or do this. It's not really walking. It's really like you imagine you're on ice and holding onto something and then pushing against it. That's basically how it feels like. But it works in the sense that, okay, yes, you can do that. And for certain game and other applications or arcades, it might actually be a cool thing to do. But it is not natural walking. But it's cool. I mean, it works. You can buy it. It's fairly cheap. There's other ones. Here's like a military application where they have a nice tether, so you can actually sit down. That's a Cat VR. There's Virtuix Omni, where you have to wear special shoes that kind of glide in there. So, I mean, it's just, I mean, for me, starting in VR about 20 years or whatever ago, it is fascinating now that finally the market has caught on and it's at a level where people get interested. There's so much creativity happening. Okay, and yes, you can also do roller shoes. There's Gate Masters. Not sure whether that works. So it's basically individual stepping platforms, but this has other issues. Or you can even have, it's kind of like your vacuum robot, basically, that kind of brings these next to you, always in front of you. So, I mean, there's lots of exciting applications, but as a researcher, I also ask, well, I mean, but is the walking really that important? So for example, do the treadmills really give you a stronger sensation that you're moving through the environment? I mean, to me, that's really important. And if you look at the actual research, no, it actually does not work. Just having even the best treadmill out there, it doesn't give you a better sensation of self-motion there. And one thing that's really missing is vestibular cues, so that you can only do on a very large treadmill where you can really walk for a meter or two before you get pulled back. For circular treadmills, it's actually different. So if you kind of step along sideways, this gives you the illusion that you're rotating. So that's quite impressive, actually. Let me skip ahead, I think. Another possibility is to use steering devices. So basically, you can, for example, go in the direction you're looking. You can use hand directions for doing this, torso directed. So basically in direction you're physically facing, which is kind of what we typically do when we walk. Leaning directed, so imagine being on a wee balance board and going this direction. Give you an example. So here's, for example, I'm not sure whether you can see that, basically using leap motion, and you can use that to control the self-motion. The nice thing about these systems, they're fairly easy to use, so learnability and so on is actually quite good. There's, of course, if you want full motion, you can use these big hexapod motion simulators. There's cheaper do-it-yourself versions that you can use, but it's not quite as easy to do. Or you can even just have other people move you up and down. So that's kind of like the super easy version, basically. So this talking about prototyping, yeah, that's really rapid prototyping. Kind of the opposite of these approaches. But still, I mean, you can have, this is a simulator which also acts as a centrifuge. For example, if you really want to simulate space flight, I mean, that's basically one of the ways to go. Here's another one, robot arm. Here's a really fancy one, cable-based simulator. But what do you really do if you don't have a lot of resources? I mean, you can do it cheaper. So here's a wheelchair with some rubber bands, a potentiometer, and that alone actually gives you a surprisingly good sensation of self-motion. So we looked at this, measured that. It works a lot better than using mouse or keyboard. Another example is, let's see whether the video works. Maybe it doesn't. I'll show you. I'll have one later on. Here's one from a gaming chair which we rigged up with better motion tracking. So basically just lean in the direction you want to go. This can work fairly well, and it's interesting. You can use simple things like a Wii balance board. So you stand on that, lean in the direction you want to go. People put this whole thing on a trampoline, so you get more motion cues. It's more fun and engaging. If you do the actual research, I mean, even just leaning in the direction you want to go or while sitting can really help to give you a stronger sensation of self-motion. Here's an example where you compare different interfaces and want to figure out, okay, what is it really? So we ran a little user study comparing just joystick, gamepad, basically, and tracking this chair here where you can lean in the direction you want to go. If you want to try it out, you can come down to the booth. We have a demo of this there. Head directed, where you basically go in the direction you want to look at. You can use a swivel chair and augment this. And joystick, really, ease of use, people have so much experience with it. It works really nicely and precisely, but it's not as natural and fun as the other ones. Here's some other examples where we experimented with basically where you give yourself some motion cueing. So some of them are extremely low cost. Here's an example. If you want to try it out, it's up here in our booth, where basically you're sitting on either this device or a swivel chair and do a little bit of a gamified task. We even built a setup where you can put any chair on top and basically lean in that direction. It gets tracked, and you can use this as an interface. So, do you have 5 more minutes? Okay, good. Then I'll.
If you want to speak more for 5 or Q&A for 5, but we have to wrap in 5.
Okay, good. I'll probably show you to wrap up some flying interfaces. I think that might be good. I'll go quickly. I mean, it has been like the big old dream to do flying interfaces, and there has been obviously a huge aviation interest in doing that because you can really save a lot of money. So if you think about, okay, where is virtual reality actually useful in these kind of things, where if you crash the vehicle, it would be so expensive that it's even worth getting a simulator for a few, well, thousands or $500,000. Some of you might have tried the Burley simulator, which is, I would argue, one of the most impressive self-motion simulators where you get this kind of dreamlike experience of flying. It's still not like super, super low cost, but it's a lot of fun. Another one is from the Humphrey here, or others where you kind of strapped in. So the strapping in isn't the fun part, but once you're suspended there, it can be quite amazing, actually. So lots of interesting interfaces there. People tried Ironman style interfaces. So literally you can use gestures and fly that way. So lots of fun there. Hang gliders, another one that people tried. Base jumping. So that moment. So you really need to trust the technology for this one. Kind of the ultimate one where you don't really have any interface is basically in this kind of setup here. I think, where you can do a whole lot, but you really, really need to know what you're doing, otherwise you crash into the wall without knowing this. As you can imagine, we also tried putting this kind of any chair setup under kind of a huge stack of pillows and all kinds of different things, and seeing whether you could actually use that to get a sensation of flying and weightlessness. And that actually works fairly well. So just as a mini conclusion, like how do you really choose what interface you want to use? I mean, essentially you need to figure out, I mean, what do I want? I mean, what are the requirements? What are the functional requirements? What is supposed to do? What are the non-functional ones? So how is it supposed to feel? And then you can build up your matrix basically for different interfaces and different aspects, like what is important to you? Do you need full visual cues, auditory cues, and so on? This might look like that, depending on how you evaluate it. But there's certainly room for a lot of creativity. So final question I might get asked is, okay, here would be the link for the slides, or you can just go to ispacelab.com website and download them from there. And I think I also have this on the last slide, so this one here. All right, thanks so much.
Thank you very much, Bernhard. Awesome. We do have time for a question. If anyone has a question, potentially. Any questions? Yes, over here.
There was one thing that I've also experienced that I think is pretty common, and in some VR things, I don't know if you got the chance to cover it, but from what I remember is when you're talking about like spaces and moving around, sometimes there's areas, and then they have like these kind of virtual like kind of cage around you, right? Mm-hmm. So like.
You mean like a cave, or I'm not sure which.
Well, like.
Oh, you mean the. Like when you run to the wall, they bring up the
the virtual cage, right?
What's it called with the yes, chaperone system. Yeah. Well, this works, but it immediately breaks presence unless you somehow integrate it into your game or VR in a metaphor that makes sense.
Yeah, sometimes it can be useful. So.
Yeah. Oh no, absolutely. Yeah.
Question up front here.
Thank you. Have you looked into epigenetics? Research in how through visual input, what we consume through visual input, how it influences the change of genes?
I haven't. I think this will be kind of a long ongoing study because, I mean, well, for humans it takes a while. But in a way, what the kids currently are doing is kind of that. I mean, they look at a lot of 3D stimuli on 2D tablets and so on. So they decouple a lot of what would be natural correlation between vestibular cues and you see a self-motion. So I guess the question is really like if you see enough of the false VR or just movies and so on, do you at some point, kind of like taking off on and off glasses, do you just adapt to that? And I don't think it's clear yet. I mean, because that that takes a bit longer typically. I know that you cannot simply untrain things like motion sickness, at least not very much. You can use different strategies, but it's a really good question. And maybe there's hope, but maybe you just, the danger is that you calibrate kids to something completely different or hardcore gamers, and then they might actually feel like the real world is strange.
Last question at the back.
Hi there. I saw recently there was a study with paraplegics almost being tricked to remember how to move their legs using virtual reality setups. And I was wondering if perhaps as people who could walk, who are able to walk, would also be able to be tricked into thinking that they were moving although they were standing still while perceiving things, and maybe using brain waves to control the interface?
The brain waves don't help there. So yes, there are tricks to do that. The key thing with the paraplegics is really it's like when you're missing an arm, for example. It's the same thing. You can, if you feel like you're moving the leg and it looks like it and so on, this can help grow the connections to the leg, for example, if you're paraplegic. So this is actually quite amazing. I mean, this might be one of the most amazing applications of virtual reality. So basically, you give the motor commands to the leg that doesn't take it anymore, and to move a virtual leg, even if it's just a little bit, and your body thinks like, oh shit, that's working. Then it starts growing fiber. I mean, that's simplified. So this is really amazing. For us normal humans that are happy to be walking around still, you cannot do that. And I mean, there's brain control interfaces, but you would never want to do that. because especially like you wouldn't want to use this for driving, because as soon as you really need to focus, you need to learn this for quite some time, and as soon as you're distracted, you would be, whatever, taking the wrong turn.
Bernhard, thank you very much, and please
Well,
join me in
thanks so much.
thank you.